This is the Calton Hill Observatory at Edinburgh. It's near the centre of the city, close to the Scottish National Monument, a curious structure based rather loosely on the Parthenon at Athens. There are no major telescopes here now, but it's still used by amateurs, and it does have an interesting history. In 1822, it was created Royal Observatory by King George IV, and that meant that the director automatically became Astronomer Royal for Scotland. The first holder of that post was Thomas Henderson. Well, I'm afraid I can't show you a picture of him. Apparently, he had a very pronounced squint and would never allow his portrait to be painted. He was succeeded by Charles Piazzi Smythe. Now, he was a mixture of the genius and the crank. Quite frankly, his views about the Egyptian pyramids are best forgotten. But he did do a tremendous amount of good work, and he was also one of the very first to realize the importance of setting up observatories at high altitude. He also set up the time ball, which is here, and the time gun, which is in the castle. And every day, the time gun is fired. It's quite a tourist attraction. That's been going on now ever since the early 1860s. But when Piazzi Smythe left in 1888, the observatory was, quite frankly, in a bad state of repair. And the situation was rescued by the Earl of Crawford. He suggested building a new observatory and donated instruments and books from his own private observatory outside Aberdeen. The new observatory was then built at Blackford Hill, then on the outskirts of Edinburgh. Why was it decided to build the observatory here on Blackford Hill?
Well, it was a compromise, really. They wanted somewhere that was well away from the city centre, so you could get away from the city lights and all the smog and pollution from the chimneys. But they didn't want to go too far. They could have gone way out into the middle of nowhere. There's plenty of mountains down to the south, which would have made good sites for observing. But it would have been very expensive to construct and to staff a building of this sort of size and complexity. So 100 years ago, it was thought that this was far enough. And there's marvellous old photographs you can see which show just empty fields, where today there's houses coming right to the foot of the hill. And the building itself is a tremendous piece of architecture. It's got all sorts of nice little features which make it a very interesting place to work. For example, you can see in stone over the entrance door the royal crest, and on the roof you can see gargoyles, even though we're not a religious institution. But the main thing that strikes you just standing here, of course, is that the building is just dominated by the bulk of the library, which was built to house the Crawford collection.
Lord Crawford presented this library along with his instruments to the nation on condition that the government would build a new observatory for Scotland, and the government of the day accepted his offer. And therefore, in a very real sense, we can say that this present observatory owes its very existence to this collection.
What are its greatest treasures?
This is the greatest treasure. It's indeed the jewel of the collection. This is the first edition of Copernicus's De Revolutionibus, published in 1543. It's the personal copy of Erasmus Reinhold of Saalfeld in Germany, and it bears his personal annotations. This is the first edition of Newton's Principia, which Lord Crawford purchased for 2 guineas. Here we have Appianus's Astronomicum Caesarium from the year 1540. This is perhaps the last major textbook on Ptolemaic astronomy published before Copernicus.
Quite apart from the historical value, is this library used for modern research?
This library, together with the modern collection, forms a continuous record of literature from the year 1200 right up to the present. The library is used by astronomers on site and by visiting researchers and the historians of science, historians of astronomy, and bibliographers.
Research today is completely different to the way it used to be. Up till about the 1950s, the observatory here spent all its time making observations with its own telescopes, looking largely at stars in our own galaxy. Since then, there's been major developments, particularly in terms of using new technology. Today, the telescopes are only part of our visitor centre, and many people come to see them, but we don't actually use them.
It's fair to say, then, that the role of the ROE today is in building and designing telescopes for other astronomers to use.
That's our main role in life, certainly. Although you must remember that you have here one of the major concentrations of researchers in the UK. We share this site with the Institute for Astronomy in the University of Edinburgh, and all told there's between 20 and 30 active research astronomers and the same number of PhD students.
Where are the main telescopes operated by the ROE now? Obviously not here in Edinburgh itself.
That's right. It became clear not long after the move to Blackford Hill that really if you wanted to do world-class astronomy you had to be looking at much higher altitude sites, and that meant going abroad. So the UK's major telescopes now are all outside the UK. They're in the Canary Islands, in Hawaii and Australia. There was the United Kingdom Schmidt telescope, which we used to run, but which is now operated directly from the Anglo-Australian Observatory.
The real basic feature of the Schmidt telescope is the fact that it has a very wide field of view. And so what you can do with the Schmidt telescope is take photographs of the sky, wide-angle photographs, and eventually build up a mosaic of pictures to get a complete survey of the whole sky. And that's the real reason this telescope was built, and that's its main job.
Why was this particular site chosen by Edinburgh?
It was chosen because essentially it's alongside the Anglo-Australian telescope, and the analogy was drawn with the setup on Palomar Mountain in California, where the 200-inch Palomar telescope and the 48-inch Schmidt had proved to be probably the most powerful and productive pair of telescopes in astronomy in the world for 20 years or so. And the idea is that the big telescope can study faint objects in tremendous detail, but you've got to know where are the objects, what are the interesting objects, you've got to find which galaxies you want to look at, and so on. And so the idea is that the Schmidt telescope surveys the sky, finds the interesting objects, and you then go to the larger Anglo-Australian telescope to do detailed study of the ones you want.
Although Edinburgh no longer runs the telescope, there are still very strong connections with Edinburgh, are there not?
Yes, the plate library in Edinburgh is a crucial part of the operation. Over the years, the telescope has accumulated tens of thousands of photographs of the sky, and these are kept in special conditions in a large plate library in Edinburgh.
As well as being the permanent archive of the plates, we also act as a lending library. Research astronomers ask us for the loan of plates, and we collect the plates as they come in from the telescope, and we would mix them with plates already in the archive and send them to them. This is usually to bases in Britain, but also right throughout the world. There's a second category of plate that comes in, and that's the plate that's taken for the sky survey. A sky survey is the systematic photographing or mapping of the southern sky. These plates come here. They are copied in our photographic laboratories onto film, such as the films on the table, and these are sold to observatories and universities throughout the world. Another of the uses of the plates is to search for the 1 in a million objects, the rare, interesting object that we want to study further. Typically, a plate will contain 1 million images, and they all look much of a muchness to the eye. So what we do is we measure them on the fast measuring machines, such as the APM in Cambridge or Supercosmos here in Edinburgh. And by analysing the measurements from the machines, we can find which of the 1 million objects might be the very high redshift quasar, the very interesting symbiotic star, or indeed which of the group of objects might be a new galaxy, such as the Sagittarius galaxy found recently.
One problem about Schmidt plates is that they show so much. Material is no good unless it's analysed, and at one stage this took so long that astronomers started to talk about the Schmidt crisis. Something had to be done, and the only answer was to analyse the plates mechanically instead of manually. And this is where a special machine called Supercosmos comes into play.
Supercosmos is a machine which takes one of those photographic plates that you've already seen produced from the Schmidt telescope and turns it into a computer image. And that means that then astronomers can do a lot more detailed analysis of the information that's on the photographic plate.
How does Supercosmos turn the plates into images that the computer can read?
The principle is very simple. We just shine light through the photographic plate. That light is then captured by a TV camera which scans over the photographic plate. The data is then processed by computer in order to detect the stars and galaxies that are present on the photograph. It takes about 2 hours or so to actually scan an entire plate, and in that time it creates about 1 billion pixels of information, and there's something like 100,000 to 1 million galaxies which then have to be detected from that data, and essentially a catalogue made of everything that can be found on the plate.
The Royal Observatory of Edinburgh is superbly equipped to analyse the plates, but it can't actually take the plates from here. There's too much light pollution and too much atmosphere above it. The best results are obtained from telescopes situated at high altitude. I'm on my way up Mauna Kea in Hawaii. This is an extinct volcano, actually taller and more massive than Everest. Much of it lies below sea level, but the summit still goes up to almost 14,000 feet, and that's quite high. Up there, your lungs take in only 39% of the normal amount of oxygen. The halfway house, just below 10,000 feet, is Halepahaku. This is where the astronomers stay when they're using the observatory. Nobody sleeps at the summit itself. It takes less than half an hour to drive from Halepahaku to the summit, but you can feel the decrease in air density. There are great telescopes here because the seeing conditions are so good. It's many years since the Dutch astronomer Gerard Kuiper proposed to use Mauna Kea as an observatory site. At the time, many people regarded him as crazy, even though Mauna Kea is extinct and the twin volcano Mauna Loa, which you can easily see from here, is decidedly active. It's now a truly international observatory with domes sprouting all over the summit, and the Royal Observatory Edinburgh runs two of the telescopes here. The first one to be built was UKIRT, the United Kingdom Infrared Telescope. I always think that UKIRT is a most impressive telescope. It looks fairly compact, and it is. It's also lightweight by conventional standards. Remember, it's designed to operate mainly in the infrared, and these wavelengths are much longer than those of visible light, so that in theory, the telescope mirror needn't be as perfect as that of an optical telescope, and it can also be thinner. In fact, UKIRT has turned out to be so good that it can be used at optical wavelengths as well as in the infrared, but that was sheer bonus. UKIRT is one of several large infrared telescopes in various parts of the world, but is arguably the most effective at the present time. As most people know, infrared comes beyond the red end of the visible spectrum. With still longer wavelengths, we enter the sub-millimeter range. This is the dome of the JCMT, or James Clerk Maxwell telescope. A sub-millimeter telescope looks more like a radio telescope than an optical or an infrared one. One of the latest instruments to be developed at Edinburgh for use with the JCMT is SCUBA, which stands for Sub-Millimeter Common User Bolometer Array. It'll produce pictures, but the JCMT isn't a visual telescope.
In order to take an image, what we do is we make an array, something like this. This is the shortwave array, in fact. It's got 91 detectors in it, and there's another one with 37 detectors as well, which are used to concentrate the radiation from the telescope. The detectors are based on a very small chip of germanium. The chip itself is very much smaller than the spot size that you get from a telescope if you focus a point source onto the focal plane of the JCMT. And in order to actually get the radiation onto the detector, we need a horn which is very much like the millimeter or microwave horn you would get in a satellite receiver dish. This is a 10 times scale model, and as the temperature of that chip rises, its resistance changes, and you can measure a voltage change. And that's used as a signal. That's used as a signal which then is fed through a series of electronics into a whole series of computers, and out of the computers at the end of the day you get an image on a visual display unit. The instrument we use at the moment on JCMT has got one detector, and in order to make an image we scan the whole telescope across the sky and build an image up very much like a TV raster pattern. Now with SCUBA we've got 131 detectors, and each of these detectors is 10 times more sensitive than the current instrument, which means effectively that we can look at the same object in 100 times less of the time. And consequently, if you think of the number of detectors we've got and that increase in sensitivity, effectively we can get a 10,000 times increase in speed. In other words, you can do a whole night's observing in a few minutes.
Nowadays, some observers don't have to go to Hawaii at all. They can detect their observations in near real time from here.
We let observers who are in Britain, who are members of scientific teams, copy data back to here using the internet and a line across the Atlantic called the Fat Pipe, and then in Britain the JANET network between universities. Because of course these days any telescope is controlled by computers, and one would never in fact have to be anywhere near the prime focus. And if you're going to be in a control room, that control room could be anywhere.
Could you tell us something about the main results coming from Hawaii?
Yes, indeed. We have, of course, a huge amount of territory there in terms of frequency space. And the spectroscopy has been very rewarding, that there are many transitions, both in the infrared and in the submillimeter, of large molecules and indeed also dust grains and ices, many of which now have also been identified with laboratory work. The second area is, of course, looking at cool objects. The holy grail of infrared astronomy has been looking for protostars. These are stars which are inexorably collapsing but not yet ignited their nuclear reactions. And mapping now with the JCMT in the millimeter has actually found some of these objects which are too cool to be seen in the infrared even. And of course, the third piece of work is that you have in the infrared redshifted optical astronomy, and some of the nicest work coming from you, Kurt, is the observation of the host galaxies of quasars.
The Royal Observatory Edinburgh has now joined forces with the Royal Greenwich Observatory, and major new instruments are being planned.
Well, it's interesting, but the next major step is one which has been in progress for some time already. In fact, before the Royal Observatories combined. It's the Gemini Telescopes project. Now, this is a project which Britain is carrying out in collaboration with the USA, Canada, and 3 South American countries to produce 2 state-of-the-art 8-meter telescopes, one in the north, one in the south. The northern telescope will be based on Hawaii and the southern in Chile, and the Hawaiian telescope will be actually run by the Royal Observatories when it's ready. It's a very challenging project. They're very fine telescopes in the sense that they will produce the best possible images. In fact, the aim in the infrared is to achieve 0.1 arc seconds, which is an astonishing achievement, with the most advanced instrumentation. And of course, with the experience the Royal Observatories have had, we're highly sought after in this process of construction. And we're making both telescope systems and instrumentation for these 2 telescopes in a way which allows us to combine our efforts, the ROE and the RGO, in a very constructive and interesting fashion.
The Royal Observatory, Edinburgh, has a long and memorable history. In its various guises, it goes back now more than 2 centuries. It has contributed much, and it still does. It's an integral part of a major astronomical complex which extends from Edinburgh to Cambridge, to Hawaii, to the Canary Islands, to Chile, and to Australia. It will remain in the forefront of research, and I have no doubt that its achievements in the future will fully match those of the past.
From tomorrow,